Okay, we had talked about adhesive bonding, and I have just got a couple of final points. At the end of the day, I said adhesive bonds require large areas for joining, and that's basically because adhesive bonds don't get rid of the contamination, they just bury the contamination. You don't eliminate oxides on metals. You might clean the surface. A clean surface will make a better adhesive bond because it gets rid of the crud, like the moisture, or you have adhesives that actually dissolve the moisture. But you got to get rid of the grease. Greases tend to be organics and they have very low surface energies, and so you got to get rid of the grease and have a clean surface. Oxide surfaces, ceramics and things like that, can have surface energies of 300, and your typical adhesives are going to have surface energies of 100, and that's in ergs per square centimeter. And so it's not a problem, but you start getting greases on there that have surface energies of 50, you can't use an adhesive with 100. There will be adhesives that are lower. But the reason you need a lot of surface energy in general is you're really just using van der Waals bonds, and therefore the strength per unit area of the adhesive joint is never going to be as good as a true joint between metals or ceramics or even among the polymers. We have things like fiberglass, which is basically just adhesively bonded fibers. We have sheets. You tend not to use adhesive bonding when you have heavy metal, like plates, because you just can't get enough bonded area in order to match the strength of a big thick plate. So it's great for aircraft and things like that. It turns out adhesive joints, because the adhesive being generally some sort of polymer or organic compound, has a fairly low modulus. If you bond two sheets together and you load the adhesive joint, you tend to distribute the stresses fairly well because the adhesive itself is compliant and distributes the stresses over the large area. You don't get big stress concentrations like you do when you put a weld in and you have, the joint goes all the way up to the edge, right? And then the edge is stress concentration. Adhesive joints basically get rid of a lot of the stress concentrators, and therefore they have excellent properties in fatigue, which is great for bonding aluminum aircraft skins or things like that. Even so, when you're riveting parts together, or sheet metal together, or adhesively bonding it together, you still got to overlap. And then we already talked about, and one of you remember the name of this new aircraft, the Challenger or something, the one that's sort of like a Learjet, and they're going to friction weld the whole skin together. Maybe it was the Premier, yeah. And that way they're not going to have any overlap. They'll just be butting things together as butt joints, so far as that goes. This is something I brought in because more and more in the automotive industry, they're trying to add aluminum to some of the sheet metal parts. And this actually is about 10 years old, but this was something that was given to me by Chrysler back in the mid-90s. They were building 6 aluminum Chrysler Neons. Neon is a small Chrysler. And back in the early 90s, Ford built a couple of dozen aluminum Ford Tauruses. And the problem with aluminum, with resistant spot welding, is the electrode life is not very good, and the quality, consistency of the welds in aluminum by resistant spot welding is not very good. So this is a case where they riveted. And in fact, in the new Jaguar, one of the new Jaguars is, or Jaguar, okay, I don't know. I'm not British, so, is all aluminum. And they used a lot of steel rivets putting it together. This is a steel riveted joint, steel rivets, aluminum, and it's got a piece, this is just an example, piece of steel and a piece of aluminum on the backside. And these are self-piercing rivets. A lot of times they'll do both riveting and adhesive bonding. One of the advantages of rivets is that virtually every rivet is a good joint. You can't say that about resistant spot welds. And so you need fewer rivets to put the whole thing together because you can rely on each one of them. But rivets are expensive. It's another part, another component, and you can see, you know, you can't put them everywhere because they're not exactly cosmetic joints that you're going to paint over. But they get around those things in the design of some of these things. So people are using adhesive bonding in automotive applications, and they've been using it for years in aircraft applications. And of course, we use it in all kinds of lower strength parts.
How much does geometry play in the adhesive bonding process? I mean, can a part be designed to have the geometry that increases so that you get 50% better?
Well, you've got to have this overlap or fibers type of thing, and so you're talking sheet metal. You're not going to build a pressure vessel that's 2 inches thick by adhesive bonding. Well, actually, I take that back. People have done such things by jelly rolling sheet metal and then adhesive bonding. In fact, it's not adhesive bonding, but the brake lines in a car are actually, rather than just using a tube that's been welded, and the problem is you don't want to have a pinhole leak in one of the welds and lose the brake line. For safety reasons, they actually take sheet metal and roll it up in a jelly roll and braze it. And now you have lots of bonded area, and the chances of getting a pinhole leak are small because you don't have a monolithic material going through the thickness. You got, you know, a lot of, you got your thickness from redundant layers of sheet metal, and the sheet metal is not going to have some inclusion or something like that. So for, you know, if you actually cross-section brake lines in a car, it's tubing, and the tubing is made by a jelly roll of sheet, which is obviously a lot more expensive than just making a tube, but for security reasons, because brake lines are pretty critical, you do that. It also gives you this layer of copper in between that gives you some corrosion resistance if the thing starts to corrode through. Pits don't run just, you know, you don't get corrosion pitting from the outside, okay, as rapidly, because you'll basically stop at the copper. So there's various reasons why people do it, but to get to the geometry, you're still talking in general thin section materials, sheets or something that might be fibers or whatever. You can't build heavy pressure vessels or nuclear reactors or things like that. Now, that's not to use, they don't use adhesive-like substances. A lot of those things, if I have to build a pressure vessel and it has to be sealed and it doesn't have to take high temperatures, I can put sealants in there. I could weld it or rivet it or bolt it. I can do other things that will give me the strength in a thick section that adhesives can't give me, and then I use a sealant material, which is nothing more than an adhesive. So it's adhesives with something else that gives it strength. But to answer your question, yeah, basically geometry does play a factor, a big factor. Whether it can be designed in or out depends on the product, okay? The big problem with most joining processes when it's not a true weld is they don't, whether it's, well, let me take that back. If you're talking brazing, soldering, or adhesive bonding, you're not getting the strength of the base material. Very rarely can you get the full base metal strength. And when that's the case, you end up with very heavy joints in your structure. Now, who cares if you have heavy joints if the part's just sitting there? But if you're talking about flying it, or, you know, the faster something moves, the more important lightweight is. So you'd rather have a true weld. And you can make true welds by cold welding, you can make them by diffusion bonding, which we're going to talk about in a second, or you can make them by fusion welding, or other solid-state joining processes. But brazing, soldering, and adhesive bonding just don't give you the full strength, and that adds weight. And that's the whole type of thing like the turbine blade, okay? They wanted to use the blisk. There's one of these, neither one of these have Christmas tree. But remember the Christmas tree structure and the big flange that you have to have on the disc? The mechanical joint always means more weight. You can't design a mechanical joint or an adhesive bond without adding weight to the structure because you got overlap. If you didn't have overlap, you'd have all that much less material, right? So, yeah, you can design it out, but can you afford to design it out in a spacecraft or something where weight is costing you $20,000 a pound? You can't really afford that. You'd much rather do true bonding, true joining. Okay, other questions?
I have a question. In sandwich structures, which proportion of weight can give adhesive? I know that's quite depends on the materials of the sandwich, but I mean, just for like a reference, ideally.
I'm not sure what fraction of the sandwich is adhesive.
Yes.
Oh, I've seen structures where 30% of the material, the weight of the material, is the adhesive in a multi-layer sandwich material. I mean, it's not all that different than a peanut butter and jelly sandwich, okay? If the bread had the same density as the peanut butter, right? But the volume of those things, again, it's only good at bonding sheets, thin sheets that are laminated materials and stuff. But the adhesives can easily be 10, 20, or 30%. I don't know that I can't think of any, or can't think of very many that ever went above 50%. But if you want to say typically between 10 and 40%, that's probably a reasonable number. Does that answer your question?
Yeah.
Yeah, okay. It's a fair amount of adhesive. I mean, take fiberglass. Well, fiberglass, in a sense, is one that is more than 50% by volume, okay? But that's not sheets, that's fibers. And I mean, even if the fibers were laid out perfectly in a hexagonal array and they were circular, all the same diameter, you'd have 30% of the spaces in between round fibers would be adhesive. Okay? If you stack up, if you were to put a bunch of pennies here and stack them up as tight as you can, 30% of the area would be the space between the pennies. Okay? So if you're talking sheet material, it's probably in the 10 to 20 to 30% range, depending on the thickness of the sheet. And I mean, rarely is your adhesive going to be thicker than your base sheets. But if you're talking fibers, it could be 30 to 50%. And if you're talking particulates, well, particulates, it could easily be 50%. In fact, typically, if I just take if I take sand and just pour it in a beaker, it's 50% dense. Actually, it's 48% to 52%. It's amazing. Doesn't even matter that much. And particle size and shape make some difference, but if the particles are reasonably close to the what we call equiax, kind of a spherical, or diameters are similar in all three directions, and that means within like a factor of 2. They're not big, long. I mean, obviously, if you throw needles into a beaker, it's not going to be 50% dense because they all line up different ways. But if you throw powders into a beaker, it's sort of amazing. You'll usually get 50% dense with very, very little scatter. Okay, and if you pack them perfectly, maybe it's 30% for spheres packed perfectly. I don't know. In 2 dimensions, for circles close packed, I think it's 71% dense, and for spheres packed, I can't remember. It's 56 or 58%. I mean, you can calculate it, but it's when you just put them in randomly and they're just different sizes and stuff, you typically get less than the theoretical of 58 or 57, whatever the number is. You get something around 50%. So for particles, it's going to be, you'll hit 50%. But it's pretty rare that you would design something that would be 60 or 70% adhesive. Okay. Other questions? Although I can think of cases where people have done it. Because if someone wants to put particles together and they want something they're going to burn the adhesive out later. I mean, I can think of metal processing things where people basically, in fact, I didn't bring it with me. I can bring it next time. There's some diamond tooling, and they basically braze it with a nickel-based powder, but they don't want too much of the nickel-based powder. And so they actually, in some cases, use a lot of adhesive to hold the nickel-based brazed powder, put the diamonds inside of that, and then they fire the whole thing in a furnace. They burn off all the adhesive, and then you have fairly widely spaced little nickel powders, and then you have, actually they have another braze alloy in there, and you bond the diamond to that, and you can end up with you want, in that case, for various reasons, you want a porous mass in some of those things. And so you add extra adhesive that kind of keeps the solid particles separated more. So there are cases where people use more, but in general, you're not going to use too much. Although the adhesives can be a fair fraction. I mean, if I've got 25% adhesive in my structure, then it sort of has the properties of the adhesive, right? can't get much better than whatever, you know, if you got 25% of your structure. That's if it's a structural material too. Okay, any other questions? Let's start talking about diffusion bonding, but to try to bring us back to the theme of surface roughness and surface contamination. With cold welding, I basically used mechanical shear to break down the asperities, get lots of surface contact, and also move the contamination out of the joint. And remember those little tandem wires, you just kind of kept on extruding the surface contamination away from the surface. And you're keeping the contamination from reforming, because even if the Langmuir is 10 to the minus 8 atmosphere seconds, you know, the atmosphere never gets a chance to hit that surface. Okay, in that case, I never separated the surface. I'm just squeezing it together. And then we went to adhesive bonding, where adhesive bonding, I'm going to interpose a liquid. And I'm not going to do anything about the contamination other than just kind of clean it, degrease it ahead of time. I'm going to allow the contamination to stay there, and I'm going to use surface energy to interpose, to let the liquid wick in between and fill up the spaces in between. And it's a fast, reliable process, not generally good for very high temperatures. Very few adhesives are any good above 200-300 degrees Fahrenheit. But most of the world we live in, we're not dealing with high temperatures. I mean, I can glue plywood together. A lot of glue used in plywood. Okay, but again, I have to worry about the cost of those adhesives. And you can go to the hardware store and you can see the difference in cost of water-soluble adhesives and non-water-soluble adhesives by just looking at the cost of indoor versus outdoor plywood. The wood is the same, right? It's the cost of the adhesive. Outdoor grade has to be non-water soluble. And so if I'm paying an extra $2 or $3 a sheet, which is 10 or 15% of the cost of the plywood, that's because the adhesives are, you know, 10 to 15% extra cost to go from water soluble to non-water soluble. I mean, it's all adhesive. It's not the equipment or anything else. Okay. Now, part of the problem that we've had over the last 15 years in applying adhesives is it used to be our water insoluble adhesives, or the adhesives that weren't attacked by water, tend to be organic or solvent-based, volatile organic compounds. Okay, I mean, you used acetone, or you used ketones, or alcohols, or something, some organic solvent that didn't react with water, didn't mix with water, was the type of thing, this solvent that could solubilize your adhesive to give it the low viscosity to allow you to form the joint. But there's all kinds of restrictions now because of global warming and things on volatile organic compounds. And so a big thing in the recent 10 to 15 years is chemists have been developing the same type of adhesives that are water insoluble, but the solvent that you apply them to the surface with is water-based. Sort of a contradiction in terms. But basically what you have is you have little polymer particles, and then you have to put a polymer monolayer of some other thing, basically a soap type of thing, that attaches to the nonpolar adhesive particle, and then has a polar end that will allow it to be dispersed in water. I mean, water is a polar molecule, and so it needs polar groups if it's going to dissolve something. Most of these water-insoluble adhesives are nonpolar, and that's why they're hydrophobic. Okay, they don't like water, and so now you have to put something on the surface of that, and then you have to do something such that whatever that is doesn't interfere with the surface energy of that adhesive. And so it's some pretty clever chemistry, if you will, to start taking nonpolar adhesives, which are making them into little particles, and then putting a monolayer of some sort of compound on there that essentially makes them look like they're polar, so they can be dispersed in water, so that when I apply the adhesive, it spreads out across the surface. With water, the water evaporates rather than volatile organic compounds, and I don't destroy the ozone layer. Okay, so there's always something else for the chemist to do in developing adhesives. Okay, diffusion bonding. Since we're looking at different ways to try to get rid of these surface asperities and the surface contamination, one thing is to just apply pressure with heat. I mean, cold welding was just applying pressure. But in order to cold weld, we had to have interfacial shear in order to break things down. In diffusion bonding, I don't have to have that shear, and so I don't have the same type of geometric limitations to my part that it can tolerate, you know, extruding and surface upsetting. I actually can make diffusion joints where I just squeeze them together and there's hardly any mechanical upset of the part. So I can machine very precise parts, hold them together very tightly, and not have very much deformation, at least on a macroscopic scale. But on a microscopic scale, that heat will allow me to deform the asperities and get large areas of contact. In addition, the heat will allow some diffusion, so the atoms move and essentially eliminate the valleys and the mountain peaks by atomic movement. Okay, so some of it's pressure to deform the asperities, some of it's time at temperature where the atoms rearrange themselves to eliminate the pores, and we'll talk about that in a second. And the heat also helps you eliminate the surface contamination. Well, for example, in gold wire bonding, I mentioned we often do it not cold, but warm. You heat it up to a couple hundred degrees Fahrenheit, and you drive off the moisture, and you drive off some of the organics. I mean, you may not realize it. There are organics all over this room. Each one of us is emitting organics from our body. And remember Linus and Pigpen in Peanuts? Well, if you could, and actually there are techniques where you shine laser light at a funny angle. Actually, you've seen Tyndall lighting. If you've ever looked in the sun coming in a window and you see all the particles of dust in the air because the angle of the light coming in, you can do that with lasers and stuff, and it just makes the very fine particles, you know, light up and look huge. If we actually did Tyndall lighting as someone was walking around, or if you've ever seen a picture of someone sneezing with Tyndall lighting, it looks like, you know, they just emitted about 10 pounds of liquid in the room, but it's actually very fine drops, and it's just glowing because of the light. But nonetheless, it's pretty dramatic. We are emitting things. Trees and plants are emitting things. Trees, I mean, there's all kinds of organics in the air from trees. You walk through a pine forest, and you actually could get kind of resiny if you were there long enough, okay? So there's lots of things to contaminate the surface, and warming things up just a little bit gets rid of the very weakly bonded ones, the water vapor and the greases and oils, and you can get rid of those at 200 or 300 degrees because they're just physically absorbed on the surface, and you kind of boil them away in a sense, or evaporate them away. But if you go to high enough temperatures in some of these metals, when you're going to 1,000 degrees or 1,500 degrees, you actually can start to diffuse away the oxides. And there are some metals that are particularly good to diffusion bond, and things like iron, copper, nickel, and titanium are excellent for diffusion bonding because they will dissolve their own oxide. In fact, this ability to dissolve its own oxide is a bit of a problem in titanium in the sense that if you get to 900 degrees centigrade in titanium, the protective surface oxide in titanium will diffuse into the titanium. Titanium will dissolve oxygen quite well, and at 900 degrees centigrade, that oxide just diffused into the titanium, and now if you actually are exposed to the air, you put titanium in the air at 900 degrees centigrade, and it'll ignite, and you'll have a sparkler. And the adiabatic temperature is like 3,000 or 4,000 degrees centigrade. Now this has happened a few times in some jet engines, in the compressor section of the engine. The compressor section should never get that hot. It should be like 900 degrees Fahrenheit, not 900 degrees C, okay? But there have been some cases where there's been some upset and the titanium compressor parts got to 900 C, the titanium ignited because I got, 30 or 40 psi air, okay? Things burn really well, at 40 psi air, right? There's a lot of oxygen in that, right? And the engine's just, like, in seconds, the whole thing is fried, and you just got ashes left over. It's not so good, but, and in fact, about 10 years ago, it was a big deal. They had a couple of titanium fires, and we talked about aluminum fires in the Sheffield, and did we talk about that in this class, or was that in my other class? Oh, we didn't talk about that. Okay. I mean, about metal fires, right? In the sense of aluminum can burn. Okay, the Belknap disaster, right? Do I have to go through the Belknap disaster? Actually, Stefano probably doesn't know the Belknap disaster. Do you guys know it? Okay. Let's see if you want me to tell it or you want to tell it? Okay, well, you can tell me if I get it right.
You'll probably tell it with a little different spin on it than I would.
Okay. Well, the Navy was having some maneuvers, and there was an aircraft carrier, and there was a destroyer called the Belknap. And the Belknap, for whatever reason, was too close to the carrier, and there was a small collision. It wasn't even as I understand, it wasn't a big collision. But when it happened, they have these elevator decks or whatever that carry the aircraft from the maintenance deck up to the flight deck. And the Belknap actually collided with one of those things or whatever, and some jet fuel leaked down onto the aluminum superstructure. Okay, at that time, this is back in the 80s, right? And you basically you have aluminum metal, but you also, part of the ship is steel, and steel is basically rust. I mean, that's what sailors spend 30% of the time doing, is chipping rust, okay? If you take this reaction and you get a little bit of heat to get it going, you can burn the aluminum with this oxygen, and you will end up with iron plus aluminum oxide, and I'll let you balance that equation. Use some coefficients in front, right, to balance the equation. You get a lot of heat. In fact, this is called thermite welding. No, that's called a drill underneath this. Putting an air conditioner in, that'll be great. In any case, they had some jet fuels leak, and it caught fire, and it's ignited a thermite reaction. We have to talk to him. In fact, well, we only got another 20 minutes. That's going to destroy the tape. To get this thing started, but it doesn't take very much, okay, in a small area. And it's, if you've ever, well, you guys probably haven't seen a thermite weld, but a thermite weld, you can have a container this size full of this powder, which is almost dirt cheap. It's just iron oxide and aluminum. And you ignite it, and within 5 seconds, the whole thing heats up to around 2,000 degrees centigrade. The iron that you end up, reducing forms a molten mass of iron, and then typically what they do in a thermite weld, you have this big chamber full of the powder, and you have a gap down here, and just put a piece of aluminum foil, not really foil, but aluminum sheet down here. When the molten iron hits the aluminum sheet, it just melts right through it. And so that's your valve to allow the molten iron to come through. And you end up, down here, you'll have a mold. And typically, one of the things that you will weld like this in the field is railroad rails. Okay? And so you have two railroad rails that might be spaced by a 1-inch gap. You put some sand molds that are shaped to the railroad rail sides. So now you have a 1-inch wide gap, and it's backed up by the sand molds. You put this little bucket, this ceramic lined steel bucket full of the powder inside. You ignite it, and you wait 10 seconds, and it drops through the aluminum sheet, and you made a weld. And they're almost good in some cases. Turns out, although you have some superheat, you have to preheat the railroad rails on either side, and sometimes you get a lack of fusion because the stuff cools too quickly against it. Turns out you have about a 50% chance, typically, of getting a good weld with a thermite weld, but it's sort of a losing proposition if you think about it. If you want to weld steel rails together, I mean, the equipment's very cheap. It's very easy to do it in the field, to weld this big, heavy steel rail. But the problem is you go and then do non-destructive testing, and you find that half the welds you make are defective, and you have to re-weld them. Well, if you have to re-weld them, it means you have to cut out the weld. It means you have to put 2 welds in, because you have to put a splice plate in. And there's a 50% chance of each one of those being bad. So it's sort of, it does converge. The series converges, but not quite fast enough. Right? So you just keep on repairing these things. Anyway, so that's basically what happened on the Sheffield. The Sheffield just wiped out the ship as well. Okay, and they've had jet engines with titanium catch fire so far as that goes. I have a situation where some guys about 4 or 5 blocks from ground zero, about 2 months after ground zero, where they went in the bottom of basement of like a 60 or 70 story skyscraper in New York City. They had a titanium heat exchanger, and they went in there. They had a problem with corrosion. They had screwed up and got some of the East River into where it shouldn't have been, and anyway. And what's more corrosive than the East River in New York, right? Anyway, they had to remove this heat exchanger, and it's a great big thing, about the size of this room. And so they went. It turns out the tubes in the heat exchanger are made out of titanium, and you can flame cut titanium. However, you have to be careful, and they noticed that when they were flame cutting titanium, that every now and then they'd get little fires start. Well, it turns out titanium burns really well in air, because titanium forms a stable nitride and a stable oxide. So you can oxidize titanium with both the oxygen in the air and the nitrogen in the air. All you have to do is get it above about 900 degrees C. And they found that since these were little tubes and they were flame cutting them, they just had a garden hose there, and they found they hit it with a garden hose, and that was pretty good. It would put out the fire for the first couple of days. The problem is titanium will react with water to form TiO2 plus hydrogen, and hydrogen will burn, right? So on the 3rd day, it was a Saturday morning, they were doing this, and all of a sudden they hit it with the garden hose, and the flames wouldn't get bigger because the water was producing a fuel. Okay, the titanium was reacting with the water to form hydrogen, and so they tried to put it out for a couple of hours, and finally they decided to call the fire department, and finally the fire department gets there, and about 20 minutes after the fire department gets there, they have a minor hydrogen explosion in the basement that does about $10 million worth of damage. So anyway, but it's because these guys were flame cutting titanium, and they thought it was kind of curious that, the titanium would start fires. They didn't even stop these clowns. Anyway. So these things are good for diffusion bonding because they don't form, or they will dissolve their own oxides. But there are other things like aluminum and magnesium which don't dissolve oxygen. The solubility of oxygen is near 0 in those metals, and the oxides are extremely stable. Aluminum and magnesium melt at around 660 centigrade, both of them, one 650 and magnesium 650 and aluminum 661 or something. But their oxides melt at 2,000 and 2,800 centigrade. Okay, this one's almost 3,000 centigrade. And so it turns out they're extremely difficult to diffusion bond. It's not you say you can't do it, but they're very difficult because how do you get rid of this contamination? The heat doesn't just get rid of this contamination for you, okay? One of the things you have to worry about is formation. When you're doing all this, things are diffusing, the atoms are moving, and I might form brittle intermetallics. And to give you an example of, well, I'll give you an example later when we get to transit liquid phase diffusion bonding tomorrow. You use inserts sometime because a lot of times diffusion bonding is very good in many cases for joining 2 dissimilar materials. And a lot of dissimilar materials you can't just fusion weld because in the liquid states they're going to end up forming an alloy that's doesn't have decent properties. So you like diffusion bonding because it's a solid state process. But sometimes you have a problem, like I had a paper at one time where people were trying to bond a refractory metal to aluminum. Well, it turns out you can't do that because the aluminum melts at such a low temperature and the refractory metal doesn't really soften until such a high temperature. They needed to basically put an intermediate surface on there, and they bonded a different material, like nickel it might be, to the surface of the refractory metal, and then you could bond the nickel to the aluminum or something by some other technique. Another thing is, it turns out these are refractory metals, tantalum and vanadium form intermetallics. They can be brittle. So if you put niobium, which is another refractory metal in the same part of the periodic table, you put it in between, a sheet of niobium in between, and it solves the problem because it doesn't form intermetallics with either tantalum or vanadium. And so basically you just got this layer. So it's a peanut butter sandwich with the niobium in the middle to avoid the brittle intermetallics. So you use, also sometimes you use these inserts to relieve thermal expansion stresses. I got two different dissimilar materials. If there's too big a difference in the thermal expansion coefficients we talked about in making electronic packages, you'd have the silicon up here, and then you'd like to have copper to suck the heat out, right? The new Apple G5 2.5 gigahertz computer is liquid cooled because you can't get enough gas through there to cool it. Okay, you need the extra atoms of the liquid to carry the heat away. You'd like to have copper, but the difference in coefficient between copper and silicon is so large that you would just crack the silicon. Okay, so they make tungsten copper composites, and the copper gives you the thermal conductivity, and tungsten has a low coefficient of expansion. Very expensive composites, very heavy. And so one of the things they make nowadays is they make silicon carbide aluminum composites, which you can match the coefficient of thermal expansion of that to the silicon and end up without the big problem. And you've got aluminum, not quite as good as copper for pulling heat away, but not bad. And it turns out silicon carbide has reasonable thermal conductivity as well. So you can put inserts in between to relieve residual stresses. There are problems in diffusion bonding. High pressures mean high fixturing costs, okay? Long diffusion times. The high fixturing costs and the high pressures, the typical pressures you're going to need are something on the order of 5,000 psi. You got to break down these asperities. And the metals you might be trying to diffusion bond might be nickel-based alloys, superalloys, that have a strength at room temperature of 200 ksi. And you heat them up to high temperatures, well, they still have 100 ksi strength. After all, they're high temperature materials. That's what they're designed for. So even at the bonding temperature, these things, even though you're above the operating temperature where they have 100 ksi, they may still have 60 ksi strength. I got to have high pressures to start deforming those asperities in some of these things. And that means really high fixturing costs. The fixtures can cost more than the parts. I don't remember if it was who asked me, but I brought in that first day a part of the X-33 space plane, which actually was an adhesively bonded structure. But the fixturing cost for that composite material is a $50 million structure, and I think the fixturing costs were $37 million of the $50 million. Okay? They just made great big steel frames. This is just for adhesive bonding to go in an autoclave at about 300 degrees. One of the tricks, since a lot of these parts that you're diffusion bonding may go into a jet engine, one of the tricks is you may start with something like a big molybdenum ring. Molybdenum is a high temperature material, and put it on the outside, and then you put something like stainless steel or something on the inside, or some nickel-based alloy, and then you make this, you put the donut, your part, in between, and the thermal expansion, the lack of thermal expansion of the molybdenum on the outside, and the larger thermal expansion of the nickel on the inside, squeezes the part in nice symmetrically, and it's sort of self-fixturing. That's a cheap way to do it, although molybdenum might cost you $15 a pound, okay, and you're just making a ring out of it, but you can reuse it, okay? But the fixturing costs can be very high in order to get these pressures. Long diffusion times. Typically, we're talking about diffusion times of, it can easily be 24 hours, something on the order of a day, could be 2 days, could be 10 hours. Diffusion is a slow process. You're limited to temperature ranges between 6/10 and 8/10 of the melting point. That's in Kelvin, or sometimes the diffusion folks like to call it the homologous temperature. Homologous temperature in this case just means the temperature of the melting point. The temperatures also that you have to process this at high temperatures will eliminate any beneficial effects of thermomechanical work. A lot of the high-strength aluminum alloys get their strength because I heated them up, quenched them, solutionized them at a low temperature to get precipitates. If I go above the solutionizing temperature to do the diffusion bonding, I just wiped out all my beneficial effects. HY80 is quenched and tempered steel. I can't diffusion bond HY80. It won't have the properties afterwards. I'm going to have to completely reheat treat it after I do the diffusion bond. So typically because of this, well actually because of all of these things, and we already talked about the stable oxides of aluminum and magnesium, because of all of these things, you tend to do diffusion bonding on very high value-added parts. Fixturing costs, long diffusion times. A furnace, a vacuum furnace for diffusion bonding, my rule of thumb, which is a very crude rule of thumb, is $1,000 an hour, okay, to run a vacuum furnace industrially. Now we're talking a fair-sized furnace. It might be half the size of this room. You can put a fair number of parts in it. But for the vacuum equipment or the atmospheric controls and everything else, first of all, the furnace probably cost $1 million to begin with, and just amortizing the capital costs. But then the operating costs and the maintenance, it's going to run about $1,000 an hour. So heat treatment is not cheap. Even if that was a furnace for just heat treating pieces of steel, it may be $1,000 an hour, but the nice thing about that, the part's only in there for an hour to do the heat treatment on the steel. Diffusion bonding is in there for 24 hours. So you run into some problems there in terms of cost. You have to have something that's going to can go to these types of temperatures and maintain its mechanical properties. Well, that tends to be high temperature materials anyway, things that were intended for high temperature. So it turns out that we're talking typically aerospace parts that have values, added values that could be $200 or $1,000 a pound or something like that. You're not going to diffusion bond automotive components, which have an average value of about $2 a pound, okay? Because it's an expensive process. To give you some idea of types of things we do use diffusion bonding for, well, actually, I really should save that for transient liquid phase diffusion bonding. Here's this is an example. I passed this around on the first day. This was a prototype. It's a piece of titanium, and they took two pieces of titanium sheet and they machined them and they squeezed them together. The bond line is right down the center here, and then they put them in pressure. Basically, they put this for fixturing something like this. They actually seam welded the ends to close it. And something like this, they actually put it in a high pressure furnace, what we call hot isostatic press, where we have argon at 20,000 psi or 15,000 psi, I mean maybe only 5,000 psi, and you heat it up in this high pressure argon, and the argon does the fixturing here. Okay, it gives you the pressure. However, that furnace, probably 24 hours at $1,000 an hour, and so you're talking $24,000 for your heat treatment costs to make parts. This was a prototype development for one of the compressor blades for the F-22 engine. Okay, someone who worked on the development program. Okay, this is just kind of a little laboratory sample to show people, right? But it's a diffusion bonded part. They also use titanium is so nice to diffusion bond, and when you go to some of these kind of self-fixturing things where you just you can apply gas pressure on the inside sometimes. I mean, if you seal this, you may not need the gas pressure on the outside to hold it together. This one you had to have gas pressure on the outside because that's where the joint, you got to squeeze those joints. But there are other cases where I have a big cylinder, and for example, the Air Force builds aircraft frames this way. So they've already got an outside frame, but they want to bond some of the structural components to it. This might be a titanium part on some fancy aircraft. And they basically end up creating something where they pressurize the inside and squeeze the titanium on the inside up against some outside ring, which is also the part that you want to bond to. And so you're getting the pressure from a gas pressure internally on that. And it turns out titanium's nice because you can get something called superplastic forming. Titanium and steel both are materials that have a crystal structure change as you change the temperature up and down. At some intermediate temperature in steel, it's about 900 degrees centigrade. And if you cycle between that, you can get very, very fine grain size. It turns out very, very fine grain size means that the material will creep or plastically deform, hopefully without fracturing, to very large strains. I mean, you can get 200% strain in a superplastic material. In fact, I should have brought it. I have some of the original 1960s superplastic aluminum zinc alloys downstairs. I'll have to remember to bring it tomorrow. But you can take titanium, make it fine grained so it will superplastically form at high temperatures, and you basically make it into a system where you blow it up like a balloon inside a chamber that is something you want to bond to, and you will essentially, they call it superplastic forming diffusion bonding, SPF-DB, and the Air Force 10, 15 years ago put millions and millions of dollars and got a tremendous payoff to make near net shot parts by doing diffusion bonding. Because now the furnaces might be expensive, but you end up building some titanium frame of the aircraft that might be, half the size of this room or something, and you put it in a furnace, so big deal. The whole part's worth $500,000 when you're all done. Who cares about a $24,000 heat treatment? Okay, but it's clever design and fixturing. You were asking earlier about adhesive bonding. Can you do some things? Well, in diffusion bonding, they do some pretty clever things in the designing for self-fixturing, if you will. Okay. So now we'll tell those guys they can go back to work. They're putting an air conditioner in my lab. Isn't that nice? MIT's paying for it. I couldn't believe it. I didn't know they paid for anything around here.